So if we talk about electrical power, we're going to first want to talk about just power in general. We know power is how much work we do in a period of time or how much energy in a period of time, and we get our power in watts, joules per second. If we talk about electrical power, it's important to be able to distinguish what's going on with electrical power. Let's say we have an electric field going from left to right, and let's say that we have a charge here. So the voltage, right, is how much work is done per unit charge, and we've talked about that quite a bit. How much work done per unit charge is voltage. And if we rearrange the equation and we multiply the potential difference or the voltage by the charge, we'll get how much work is done, right? We know that the power is how much work in a period of time, right? So if we place this in here, voltage times the charge and a period of time, we can describe electrical power. It's the power dissipated in the resistor in moving a charge Q across it in time t. And that's a way that we can define it. It's the power dissipated or used up in a resistor or something that is taking it up and has, everything has a certain amount of resistance, moving a charge in time t. So, we have our new value there. And so if we think about it, right, VQ, we have that here. Q over T, how much charge in a period of time, is I. So this is how we calculate electrical power. It's the current times the voltage. And that's why that is. It comes directly from what we've known about power. All right, so if we talk about EMF, electromotive force, we have a certain amount of work per unit charge, right? So if we divide the top and bottom by time, we'll have a work over time and Q over time, right? Which is fine. We can do that. So we'll have power per unit current. And so EMF is the power provided by the battery per unit current. And that's a way that we can define EMF, and it'll be important to remember that. So power provided by the battery per unit current. All right, so we've already derived the power equation, current times voltage, to get power. And if we use Ohm's law, we can, rearrange this to get what we need. So V equals IR, right? So if we want to, instead of using voltage, we could place this in for voltage. And then we would have I times IR, right? Which would be I squared R, is equal to the power. So if you just have resistance and current, you can figure out the power. Or if you rearrange the equation, V equals IR, and we can replace this in for current, V over R. We place this in for current. We would have V over R times V. So we'd have voltage squared over resistance will give us the amount of power. So how much current flows through a 100-watt light bulb connected to a 120-volt DC power supply? So if you want to pause the clip and give this a try, you can do that, and then when you're ready to check, you can hit play to continue. Okay, so our current is 0.833 amps, and we can find the resistance here. We know the current, and we know the voltage. So we can find the resistance of this bulb at that particular voltage, and we get 144 ohms. Okay, so how many kilowatts of power does a computer use if it's connected to a 120-volt source and has a total resistance of 175 kilo ohms? So I'll let you go ahead and try this one. You can pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so 120 volts, we've got a resistance, and we can find our power this way. So 0.08229 watts, and we convert to kilowatts, and that's how many kilowatts we have. And then after an hour, how much do we use? So you can try that as well. So go ahead and pause the clip again and give that a try, and when you're ready to check, you can hit play to continue. Okay, so 3,600 seconds, and we have our power and which we would need to use the original wattage, and it would be using 296.23 joules in an hour.